Let's move on and see what the final version of an atom is, which is the Schrodinger's model of the atom. And this is, again, if you take quantum mechanics, you will spend quite a bit of time on the mathematics behind that. That involves, differential equations and vector calculus that many of you may have not taken. So we're not going to deal with it here. It's not so complex, honestly. Once you do this math, you could probably follow along. But at this moment, where many of you have not even finished your calculus sequence, we're not going to bother doing this. Okay. So at the moment, to you, it would be very complex. To you in 2 years or 3 years, it will be a little less complex. All right. So these are equations that try to describe where the electrons hang out around the atom. So you can think of it as a model of what the atom looks like, and this is our best guess to this day of what the atom actually really looks like, and it's a pretty good model. So we stick around with it. Okay. Electrons hang out in orbitals, but they don't track orbits like I showed you a second ago. They're not like planets around the sun. That doesn't work like that. They're located in clouds. And we're going to describe these clouds where they like to hang out with 3 variables, N, L, and M. Okay? And let's go one by one and describe what they are. N is known as the principal quantum number. Okay? And one quick note, I will belabor the junk out of this. We will have multiple slides here that describe the same thing over and over again. So pick your explanation and stick with it. If you understand me after this slide, tune me out. If you don't follow along, I'll do it from another angle. But hopefully you'll understand it by the time we're done with this. N is the principal quantum number. It's a positive integer. So it's going to be 1, 2, 3, 4, 5, whatever. And it tells me the size of this cloud. Okay, where this stuff is, how big it is. So is it this big, or is it even larger or larger? So 1 would be a small cloud, 2 would be a larger cloud, 3 would be an even larger cloud. All right. Now I have another number, quantum number called L. All right, and this is going to be the angular momentum quantum number, and its values range from 0 to n-1. Okay, so meaning what? That if n is equal to 1, L can only be 0. Okay, if n is equal to 2, it could be 0 and 1. All right, and we say that if L is equal to 0, we call that S. If L is equal to 1, we call that P. L is equal to 2, we call it D. And L is equal to 3, we call it F. So this Spedifa. And this tells us the shape of the cloud. So this is the S orbital. So L is equal to 0, L is equal to 1, L is equal to 2, L is equal to 3. These are the most common shapes. We're not going to do more than L is equal to 3. We're not even going to do L is equal to 3, to be honest with you. We'll do L is equal to 0, 1, and 2. 3 are those lanthanides and actinides, so we don't really bother with them. And there's more, but we don't really deal with it. It's theoretical chemistry and physics that we just don't deal with. So focus on Spedifa, and it tells us the shape. P looks like this, D looks like this. If I have S is equal to 2 and it's a P, it's a larger double egg than if it's if it's N is equal to 1. Okay, N is known as the shell number, and L is known as the suborbital, which we'll see to in a second. The subshell. Okay. M is going to be the magnetic quantum number, and it tells us the orientation of the orbital, and its values go from negative L to L. And the fourth quantum number, which I'm mentioning for the first time, is here is spin, is just negative 101. Okay, your head's probably spinning. Let's discuss this. Let's dissect it from another angle. All right. I have here all the orbitals you'll probably see, and then some. All right. The lowest orbital you'll see is 1s, then it's 2s, 2p, 3s, 3p, 4s, and so on and so forth. What does this mean? Here I have n is equal to 2. Here I have n is equal to 1. Here I have n is equal to 3. These three guys. N is equal to 3. Okay, so within n is equal to 2, that's the shell. Okay. I have 2 subshells. Hey, go with me. To have 2 subshells. This is the subshell S, which is L is equal to 0, and L is equal to 1, P. 2 subshells, S and P, all right? And as a reminder, N is equal to 2, meaning that L can only go up to 1. So it could be 0 and 1. So therefore I have S and P, 0 and 1. All right. I have that here as well. Go away, orange. So here I have shell 3, and shell 3 can have L is equal to 0, 1, and 2. Okay, so S, P, and D. For shell 4, I can have L going from 0 to 3. S, 0, P, 1, D, 3, and 2, and F is 3. So I have 0, 1, 2, and 3. So for the fourth shell, I can go all the way to F. And then for the fifth shell, I can actually go on to G, but we don't deal with that. That doesn't happen. So don't worry about that. We're going to go all the way up to F, if that even. We're probably not going to get here. All right, so that's S and P. So hopefully that made sense. Okay, and instead of writing 2, 0 and 2, 1, I have letters for it, 2S and 2P. Okay, so that's the N, that's the L. Okay, so you can think of it as 2, 0, 2, 1, and here 3, 0, 3, 1, 3, 2. But it's confusing, so we just give it letters. All right, every one of these subshells can have horizontal lines there. Okay, these horizontal lines, which we call orbitals. Right. How many horizontal lines? That's dictated by M. So don't worry so much the fact that the M is -2, -1, 0, 1, and 2. Just how many there are. All right. So M for L is equal to 2. I'm allowed to go from -2 to 2. So I have 5. So for L is equal to 1, I'm allowed to go from -1 to 1. So I have 3. And for L is equal to 0, I'm allowed to go from 0 to 0. So I have 1. So all of that M is saying, don't worry too much about the actual number. The number -2 means nothing to you. All that you need to focus on is that all D's have 5 orbitals. All P's have 3 orbitals. All S's have 1 orbital. Okay, that's what you should focus on the most. All right, not so much these numbers, but although I will ask you in homework questions to list this out. So do know this. But you won't apply this. You won't need to. You just need to know how many there are, really, practically speaking. So, okay, so I have my subshell, I have my shell, I have my subshells, I have N, I have L, and M tells me how many lines or orbitals each subshell has, okay? So if I'm looking at it here, N is equal to 4, L goes up to 3, so -3, -2, -1, 0, 1, 2, and 3, so I have 7 of them. Okay, so that's what that means. And do I have S? Yeah, each horizontal line is equal to S. To orbital, S just tells me how many orbitals I'm allowed, how many electrons I can throw into each one of these orbitals, which is always 2. So I can go up to 2 in each one of these. So that's why I'm not focusing too much on S, which is the spin. All you gotta know is that each orbital can have 2 electrons. So I can have 2 here, 2 here, 2 here, 2 here, 2 here. So P can have 6 electrons, S can have 2 electrons, D can have 1, 2, 3, 4, 5, 10 electrons. Okay, F can have 14 electrons because it's got 7 lines. Okay, that's what that is. All right, let's belabor it even more. So each shell N has N subshells. So N is equal to 3. There are 3 subshells. It has N squared orbitals. So N is equal to 3 has 9 horizontal lines, and each can occupy 2 N squared electrons. And the values of L, L is equal to 0 is S, that's 1 orbital and that's 2 electrons. L is equal to 1, that's P, 3 orbitals, 6 electrons. L is equal to 2 is D, and it's 5 orbitals, 10 electrons. And L is equal to 3 is F, 7 orbitals, it's 14 electrons. Okay, so now that we did it 100,000 times, let's try to describe the one shell. We will do this 2 shell. The first of all, the 1 shell, what is that? N is equal to 1. That's the first shell. That's what that means. We'll start with 1. The first shell is N is equal to 1. So N is equal to 1. Great. L is allowed to go all the way up to 1, but not 1. Because L could go from 0 to N minus 1, meaning L is equal to 0 or S. We're going to call it S instead of 0 because otherwise we'll have 1, 0. Or 1 S. All right. And M can go from negative L to L. Well, L is 0, so it should only be 0. So M is equal to 0, meaning I have 1 orbital. So draw the orbital. That's the 1s orbital. I can have that, and I can have 2 electrons hanging out there. Let's describe the second shell. Second shell, I have n is equal to the second shell, which is 2. L can go from 0 to n minus 1. So L could be 0 or 1. So S and P. So I have 2 subshells here. I have 2S and 2P. And M can go negative L to L. So I can have negative 1, 0, and 1. So let's draw the orbitals. 2S is this. So for L is equal to 0, I can only have 1 orbital. For P, for L is equal to 1, I can have 3 orbitals. 1, 2, 3. So that's what that would look like. Okay, so that's the second shell. All right, electron configurations. Now what I could do is I can use these orbital diagrams to assign electrons for every single element that I have. So let's look at an example. Sodium has 11 electrons. All right, let's draw a bunch of orbitals together. So I start with 1s, then my second shell will have 2s and 2p. My third shell will have 3s, 3p, and 3d. Don't worry about 3d, we're not going to reach it. Each one of these lines can house up to 2 electrons. Okay, so let's fill them in. Each one should get 2 electrons. So 1, 2, okay, so 1 goes up, 1 goes down. That's the 2 s's. 3, 4, 5, 6, 7. You can see they're all going up first. 8, 9, 10, 11. This is my electron configuration diagram for sodium. 11 electrons. Each orbital has 2 electrons. They each have opposing spins, and they go up to the number of electrons that I have, which is 11. I draw this, as you can see, when I'm reaching the p orbital, and when I do the d, it's the same thing. I put all the ups first, and then I put the downs. Okay, that's how you would draw that. So if it was an element that only had this many electrons, 6 electrons, it would look like this. I would say 1, 2, 3, 4, and then you do 5, 6, rather than have a down electron here. That's not how you do it. You do the second orbital here. 2 of them will be up. Okay, so I can write it like this. Now instead of writing these things every single time, I can write it like this too. It's much easier to write out. 1s2, 2s2, 2p6, 3s1. If you go to Wikipedia articles, by the way, for any of the elements, they will tell you the electron configuration for every single one of these. So you have that too. And they're constant. For every element has its own. Oh, I just mentioned it. The Hund's rule says that I have to do all the up arrows first and then the down. So that's called Hund's rule. Pauli's exclusion principle says that I can't have 2 up electrons in the same orbital. That makes no sense because they have this. I can't have 2 electrons have the same exact quantum numbers. That's not allowed. Okay, let's look at an example. Whoa. Which of the following orbitals is possible and which are impossible, according to the Pauli's exclusion principle? Okay, A is kosher. I'm allowed that. Each one of the orbitals has 2 electrons or 1. That's cool. According to Hund's rule 2, I didn't violate that. That's good. Here, look, I have 3 electrons hanging out in the 2s. That's not cool. In each orbital can only have up to 2. That's wrong. Can't do that. I have 2 electrons here that have the same quantum numbers. They have the same n, 2, the same l, s, the same m, which is 0, and the same s. They're both up. Okay, so this is how that would go. Here, I'm looking here. This here, I have, again, a problem here because I have 2 ups in the same orbital. That's not allowed. They have to have opposing spins. Here, I have 3 electrons in the s orbital. Not allowed. I can only have up to 2. That's not cool. Here, p can only have up to 6. 1, 2, 3, 4, 5, 6. I have 7. Not cool. Meaning that I'm forced to have 2 electrons with the same spin. Not going to happen. Here, that's good. There's no problem here. S can only have up to 2. S has only 2. P can only go up to 6. That's good. S is up to 2. That's cool. P is up to 6. That's kosher. D can go up to 10. That's not a problem. And S can go up to 2. No one's having the same N's, L's, M's, and S's. They all have separate ones. That's good. All right. Here's another way to look at it. If you don't want to memorize every one of these ways, this is how you would fill out the electron configuration. You do 1s, and then 2s, and then 2p, 3s, 3p, 4s, 3d, 4p, 5s. That's how that would work. It's not 1s, 2s, 2p, 3s, 3p. That's not how it works. So from a quantum perspective, from an energetic point of view, That's how you would fill this out. So if I have, let's look at examples and you'll see it. So carbon has 1s2, 2s2, 2p2. It ends up being that these first three. It explains why it wants to have 4 more, because P can go up to 6. So it wants 4 more. Titanium, and this will show you the Aufbau rule here. It has however many that is. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 4 is 22. So I have 22 electrons. Okay, so the 22 electrons, this can take 2, so now I have 20 more. This could take 2, so now I have 18 more. Now this could take 6, I'll have 12 more. This can have take 2, so I'll have 10 more. This could take 6, so I'll have 4 more. And sorry, I'll go here. 4s. This could take 2, and I'll need 2 more, and 4, and then I'll put that in. Sorry, I'll put that in here, 3d, and that will be the last one. So I go 1s, 2s, 2p, 3s, 3p, 4s, 3d. That's the order you would do it as, and you just fill them out this way. Okay, as remembering that S can go up to 2, P can go up to 6, D can go up to 10. I doubt you'll ever reach F. You won't need to, and this is the reason I'm not talking about G's and stuff like that, because we won't ever reach it. You won't ever reach the 8s. Don't even worry about that. Let's belabor it even more. Lithium has 3 electrons, and it would look like this: 1s2, 2s1. So I'm just following the same order as before. This can go 1 up, 1 down, 1 up, then here 1 up, 1 down, 1 up, 1 down, 1 up, 1 down, 1 up, 1 down, 1 up. And here, as I'm filling this up, these get to be in ups first, and then I'm starting to fill out the downs. So that's how you would do all these electron configurations. I think I stole this from your book. You can write them in orbital diagrams. You can write them as electron configurations themselves.